Hello, everyone. Welcome to the next talk in this morning session. We are glad to have Professor Jan Dereziński from University of Warsaw. He is an expert on quantum physics and quantum field theory. And for today, he is going to talk about propagators and curved spacetimes from operator theory. Let's join me to welcome Professor Dereziński.
First, I would like to thank the organizers for inviting me to this impressive event and for giving me the opportunity to give a talk. The subject of my talk is motivated by quantum field theory on curves, on curved spacetimes, but the first half of the talk should be understandable even for mathematicians without a background in quantum field theory or in quantum physics. Consider a Lorentzian manifold. A manifold which has a metric or a pseudometric of Lorentzian signature. So this is supposed to model our space-time, and it has there is a natural operator on functions on such a manifold, which is usually called the D'Alembertian or the wave operator. So this is it is defined by the metric pseudometric, the metric tensor G mu nu. Now you can add to this D'Alembertian a scalar potential. Typically, the scalar potential is just the mass squared. And I will call this the Klein-Gordon operator. So this is the natural generalization of the usual Klein-Gordon operator, which is well known from the Minkowski space. And one could consider green functions of this operator. So these are distributions with two variables, which where you act with this Klein-Gordon operator from both sides, you get delta functions. So they are in some sense inverses of the Klein-Gordon operator. Now, if this were a Riemannian signature manifold, then there would be essentially a unique green function, which is just the inverse of the. Then I guess this should be called the Laplacian or the Laplace-Beltrami operator, and you may add a potential, and then often this is invertible, and you have a unique green function. In the Lorentzian case, this is much more complicated and much more interesting, and this complication is relevant for quantum field theory. So this is the green functions. There are many green functions and many useful green functions of the Klein-Gordon operator. And we will also look at some B solutions. So the definition is the same, except that you have a zero instead of the delta function. So, I mean, here, to be precise, this delta function is meant to be the integral kernel of the identity operator. Now, I will colloquially use the term propagator for various distinguished green functions and B solutions of the Klein-Gordon equation, motivated by quantum field theory. So there will be the advanced and retarded propagator. These are very well-known objects from, I mean, if you study classical electrodynamics, there will be the Pauli-Jordan propagator, and also called the commutator function. In fact, the terminology in this business is very messy, and many things have many names. Now, there will be Feynman and anti-Feynman propagators. Anti-Feynman is sometimes called the Dyson propagator. And there will be two-point functions of states, sometimes called Whiteman or anti-Whiteman two-point functions. So all of these things are standard in the Minkowski. Maybe if you look at an old textbook on quantum field theory, old means from the 60s or 70s, like Bogolyubov, Shirkov, or Björken and Drell. These were the textbooks which, when I was a student, they were already somewhat old. Then there is an appendix where all these functions are listed, expressed in Bessel functions, and there is a big table with various conventions. So this author used this convention, and the other author multiplied this by I, and the other by -1. So that's it's actually a good thing to look at these appendices. Now I will try first to develop a mathematical theory how to generalize these things to a curved space-time, so to a general, more or less generic Lorentzian manifold. And it turns out that there are there are at least two distinct settings. One is the off-shell setting. Then the basic, there will be always a certain function analytic space. Here the Hilbert space will be a squared of the whole manifold. And there is the on-shell setting, where the basic space is the Krein space of solutions to the Klein-Gordon equation. A Krein space is a Hilbertizable space with an indefinite scalar product. And then I will discuss examples. Time permitting. So stationary stable spacetimes, asymptotically stationary spacetimes. There will be also some symmetric spaces, like de Sitter space and anti-de Sitter space. And many things happen. At the end of the talk, if there is time, I would like to discuss how various propagators are used in quantum field theory. In particular, the important object will be the in-out Feynman propagator. Okay, so this was the introduction, and now the first part, the off-shell setting. This is a trivial observation. The D'Alembertian plus a real function, which I call a scalar potential, is a Hermitian operator, or symmetric operator on the space of L squared of this manifold. You may object that this is not a physical space of quantum states, but okay, let's consider this mathematically. Suppose this Klein-Gordon operator is essentially self-adjoint. So you take this self-adjoint realization. Its spectrum is contained in the real line, So you can take the resolvent. The resolvent has an integral kernel, so x and y are variables in this manifold, and you can take the limit onto the spectrum, so the limit onto zero from above and from below. And this will be called the operator theoretic Feynman or anti-Feynman propagator. Now, please just accept this name now. It's not clear why this name is justified, but it is justified. We will see later that, well, there are other green functions which can be also called Feynman propagator. And the previous definition is well justified by the path integral formalism. Now, okay, let me go. So if I will assume that the manifold has no boundaries. If there are boundaries, then things are more complicated. Okay, so I hope, please interrupt me if something is not clear, but now there is another setting, so this is completely independent from the previous part. So now the on-shell setting. Assume that the space-time is globally hyperbolic. I don't want to spend time defining this. This essentially means that there is a time that flows. That there is future, there is past. It has a precise mathematical definition. Consider the space of solutions of the Klein-Gordon equation, space compact solution. Space compact means that there is a compact region and the solution propagates from this compact region. So when you intersect it with any Cauchy surface, the support will be compact. This is a natural class of solutions to the Klein-Gordon equation. Then you can define the following object. This is a conserved current. So you see this funny symbol. So this differentiates the first guy, then minus the derivative of the second guy. Now, this integral over any Cauchy surface. So a Cauchy surface, for instance, if you have time, this is a surface for a fixed time. It's independent of the Cauchy surface because this current was conserved, and it defines an indefinite scalar product on this space of solutions to Klein-Gordon equation. So because they are space compact, this integral is well defined. So we have, we have an indefinite scalar product, but if we want to do any analysis, we need a topology. Suppose we can extend this space to a larger space, which admits an orthogonal decomposition into two complete subspaces, one with a positive, that's one on which this Klein-Gordon product is positive, the other where it is negative. This will be called a fundamental decomposition. So this is essentially a definition of a Krein space. So a Krein space is a space which has a Hilbertian topology, but it does not have a distinguished positive scalar product. Instead, it has a distinguished indefinite sesquilinear form, and besides, it has a decomposition like this one written. So this is a this is a well-studied concept in operator theory. Now, suppose B is a B solution of the Klein-Gordon equation. You remember I defined it at the very beginning. So B, when you act with the Klein-Gordon operator from the left and also from the right, you get 0. Then you can each B solution defines a linear operator by this formula. So here you remember that this is this funny differentiation to both sides. It defines an operator on the space of solutions to the Klein-Gordon equation. Let us call this distribution the Klein-Gordon kernel of B. So it is not the usual integral kernel, it is the Klein-Gordon kernel. For instance, the Pauli-Jordan propagator can be defined as the Klein-Gordon kernel of the identity. I mean, identity is a very good operator on each space. And it has a Klein-Gordon kernel, which is quite complicated, but I mean, this is not a completely obvious fact, but I don't have time for more explanations. And so Pj, so P for Pauli, J for Jordan, will be this Pauli-Jordan propagator. It has many names. I mean, each researcher has a different name. So commutator function is another name. Causal propagator is yet another name. Now, the special property of the Pauli-Jordan propagator is that it has a causal support. So if 2 points are space-like separated, then the value of this propagator is 0. So it's only inside the future and past light cone. Now you can multiply this by the theta function. So you can cut only the future or cut only the past contributions. You get 2 green, here you also put a minus sign. Then you get 2 green functions. One is the retarded function. So this is the retarded function means that it propagates to the future. So it is also causal, but it, if 2 points, 2 points have to be in the not only space-like, but the other point should be in the future of the other one. Then this is the retarded propagator, sometimes called the forward propagator, and you also have the backward or the advanced propagator. So you have theta is the Heaviside function, so it is a step function. It is 0 for negative arguments, 1 for positive arguments, and in principle, you are not allowed to multiply a distribution by this continuous function, but okay, here it works. So we have 3 propagators by now, and they are very well known because they are responsible for the Cauchy problem in the wave propagation. But in quantum field theory, we need some other propagators. Now, let me define them mathematically. suppose we have a fundamental decomposition of our Klein space, of solutions to the Klein-Gordon equation. So on this, the Klein-Gordon scalar product is positive, here is negative. Let pi denote pi plus, pi minus denote the Klein-Gordon kernels of these subspaces. Let's so alpha indicates that there are many possibilities. So it is a label. So G plus alpha and G minus alpha are defined as Klein-Gordon kernels of pi plus and minus pi minus. They are, again, there are many names. They are called Weidmann and anti-Weidmann two-point functions. And they can be used to define a state, a Fock state, and so that you can quantize the theory. So many, often they are called, this G plus is often called a state, which is which is an abuse of terminology. But now, what is maybe not so well known is, so suppose we have another fundamental decomposition. So alpha and beta are two, as I mentioned, the Klein space has many fundamental decompositions. Consider two of them. Now, it is a general property of Klein spaces that we also have a decomposition, with this time non-orthogonal, into the positive part related to beta and negative related to alpha. Therefore, we can define projections, non-orthogonal projections, corresponding to this decomposition. And if we have projections, we also have their Klein-Gordon kernels. So which here there is the notation. Now we will see that they serve as two-point functions between two different vacua, and we can also introduce the corresponding Feynman and anti-Feynman propagators. Now, so given two such fundamental decompositions, we have, so now the Feynman propagator is obtained by multiplying with appropriate theta functions. That's and you can check that these are green functions. So here these were B solutions. I mean, B solutions solve the Klein-Gordon equation, and here these are green functions because when you act with the time derivative, then the delta function appears. So that's now I haven't spoken about quantum field theory, but maybe some of you, actually are well familiar. So let me anticipate what is the relationship between these objects, which I defined purely operator theoretically, and quantum field theory objects. So when you quantize the field, you get an object which is, well, mathematically it is an operator value distribution, which I denote phi hat, and x is the point in the space-time, and its commutator is given by the commutator function, or the Pauli-Jordan function. So this goes under the name of the Peierls relation, and so we have the physical meaning of the Pauli Jordan. I mean, if you have a vacuum, then you can consider its two-point function. So the expectation value of the product of the two fields. In this vacuum state, there are many vacuum states. They correspond to fundamental decompositions, and then you get this Weightman function, which I defined operator theoretically, and you can also consider the expectation value of the time-ordered product of the fields, and it will give you the corresponding Feynman propagator. Now, more interestingly, you can consider two different vacua. I mean, that's not, you can take one vacuum which is called omega alpha and another omega beta, and you can consider the kind of a mixed expectation value. Now, in order to get good identities, you want to differentiate to divide it by the overlap of these vacua. Now, and then you get the object which I defined on previous slides, purely operator theoretically, and and if you take the time-ordered product of the fields, you get the Feynman propagator. Now, you may object that there is no guarantee that this is non-zero. In fact, in interesting application, it usually is zero. I mean, quantum field theory is a very nasty theory. I mean, if something can go wrong, it will go wrong sooner or later. But on the right-hand side, you have correct definitions which were solid operator theoretical. So you can define the left-hand side by the right-hand side, and this is very useful because when you consider quantum field theory and you want to compute Feynman diagrams, then typically you want to put the Feynman diagrams on the lines, and you just put this, and don't worry that this is ill-defined. Okay, so is it okay if there are questions? Now let me give examples. So suppose that that we have a stationary spacetime. Stationary means that it can be written as a real line times some special slice, and nothing depends on time. Then it is easy to see that the Klein-Gordon operator is essentially self-adjoint. Assume in addition that the potential is non-negative. So this is called the stability condition. Then there is a prescription how to define a distinguished state on this theory, which is so in the case of Minkowski space, it is in every textbook. You just take positive frequencies and negative frequencies, and this gives you the fundamental decomposition of the Klein space of solutions, and you have a distinguished Fock state. Then you can define all these things. So the Weidmann function define the final propagator. The final propagator has now two possible definitions. One is operator theoretic, which is the boundary value of the resolvent. The other is obtained from this vacuum state. These two definitions coincide. The Hadamard condition, I think I will skip this. The Hadamard condition is a condition on states which says that its singularity structure is similar to the Minkowski case, and it is considered to be the physical condition. It is satisfied here. Now, asymptotically stationary stable spacetimes. Suppose that your spacetime is asymptotic to a stationary spacetime in the future and in the past. Well, cosmologists don't like this condition, but I'm not discussing cosmology. I'm discussing quantum field theory, and this is a condition natural for quantum field theory. So it is asymptotic to stationary. So all data has limits in the future and in the past, but in the meantime, something may happen. So now we can define two fundamental decompositions. One, the in fundamental decomposition, incoming, so the past. And the other, the out fundamental decomposition, outgoing or future. So we have two natural states, the in state and the out state. In general, they are different. Both are Hadamard, which is not an obvious statement. It is actually a deep theorem due to Gerard and Wrochner. One can introduce the corresponding final propagators. So in particular, one can consider the two-state propagator, which, the in-out propagator, so in means minus, out means plus. There is kind of a change of order. Well, I mean, so the time flows from the right to the left in formulas. That's why, and usually that's why the terminology is a little confusing. So one could define the in-out final propagator. So this one with different states from the right and from the left. Now, what about, so this is one definition of the final propagator. What about the operator theoretic one? Now, it is actually not easy to show that the Klein-Gordon operator is essentially self-adjoint. This is a difficult mathematical question. Now, it has been proven under some conditions by mathematicians, by Vasi and Nakamura Taira, but I mean these are heavy proofs. And also one can prove that the boundary value of the resolvent exists. Now, and the operator theoretic Feynman propagator coincides with the final propagator defined from this on-shell formalism. And one could conjecture that, I mean, that this should be true in much more generality than I mean, heuristically, this is always true. But yeah. Okay, so these were two examples. Now, a next example. Consider the Friedman, Lemaitre, Robertson, Walker spacetime. I mean, sometimes it is just called Robertson Walker. So this means that that the spacetime is r times the spatial slice, and on the spatial slice we have a fixed metric, and which does not change in time except for a scale factor. And so in such a spacetime you can essentially solve the Klein-Gordon equation because on this sigma, on this spatial slice, the Laplacian is self-adjoint. So by spectral theorem we can diagonalize it, and the Klein-Gordon operator can be restricted to a mode. Mode means an eigen function of this Laplace-Beltrami operator. And then the Klein-Gordon operator essentially reduces to a one-dimensional Schrödinger operator. And we know, I mean, one-dimensional Schrödinger operators, I mean, so here, I mean, here there is still the first derivative in time, but this can be removed easily. So one-dimensional Schrödinger operators are extremely well understood. So we can now again the operator theoretic Feynman propagator coincides with the in-out Feynman propagator in this setting. So the on-shell and the off-shell and on-shell setting agree. Next example, the de Sitter space. The de Sitter space is a famous model of a space-time. This is a one-sheeted hyperboloid. I mean, it can be, you can go one dimension higher, and then it can be defined as the one-sheeted hyperboloid. It is a globally hyperbolic manifold. Now, and it is often used by physicists. The de Sitter space can be interpreted as the weak rotated sphere, the-dimensional sphere, and analytically continuing the green functions, we obtain a certain Feynman propagator, which defines a Weidmann two-point function. And so this two-point function is usually called Euclidean state, or the Bunch-Davies state. I mean, Euclidean is very Euclidean because it was obtained from a sphere which is Euclidean. It has a Euclidean signature. I mean, terminology is often very unsatisfactory in this business. It satisfies the Hadamard condition and is believed to be the physical choice on the de Sitter space. Now, the D'Alembertian is essentially self-adjoint on compactly supported smooth functions. This is actually a special case of a general mathematical theorem saying that invariant differential operators on a maximally symmetric pseudo-Riemannian manifold is essentially self-adjoint. So one can define the operator theoretic Feynman propagator, as you remember, you take the resolvent and its boundary value. De Sitter space is not asymptotically stationary. So it blows up exponentially in the future and in the past. So, but sort of but it is Robertson-Walker. You can actually define something which can be called the in-out and the in state and out state with or in two-point function and now and from them you can define the Feynman propagator, and again you have the on-shell and the off-shell definitions. So the off-shell and the on-shell definitions agree. Well, what is also funny is that in odd dimensions, the in-state coincides with the out-state. This is not true in even dimensions. Anyway, in all dimensions, the in-state and the out-state are distinct from the Euclidean state. They are physically, they are bad. Actually, one can classify all de Sitter invariant two-point functions. They are called alpha vacua, and only the Euclidean state is Hadamard, which is in practice means that it is useful for physics. And all the other ones are not, even though I mean, one should think that in and out should play a role. Okay, so this was actually something which puzzled us a lot, and well, the anti-de Sitter space. The anti-de Sitter space can be defined as an embedded submanifold of the space with the signature 2, d minus 1. Actually, it is not a good model of a space-time because the time goes in loops. But this can be cured by going to the universal cover of the this loop instead becomes a line. So now we have time that flows forever. This is still not a very good space-time because particles can escape to infinity. But this is not actually this is not a serious issue for us. First, let us consider the off-shell formalism. So again, this is also a maximally symmetric spacetime. So by a general theorem, the D'Alembertian is essentially self-adjoint. There is no need to fix boundary conditions to define it. So, and one can define the operator-theoretic Feynman and anti-Feynman propagators as the limits of its resolvent. So that uniquely. Alternatively, we can consider the on-shell formalism. So we now, in order to describe the evolution of the Cauchy data, we need to define the generator of this Cauchy data. It turns out that if the mass is big enough, then this evolution is uniquely defined, even though in the classical setting, there are trajectories that escape to infinity, but quantum mechanically, there is no problem. But for smaller masses, if mass is less than some value, actually a negative value, but the boundary conditions are needed. But there is a range where there exists a distinguished boundary condition. And then there is a range where there are no distinguished boundary conditions. Now, in this range where there is a range where, again, the off-shell and on-shell final propagator, they agree. Okay, this was the end of the part where there was essentially no physics. Now, I would like to say a few words how these propagators appear in quantum field theory, which is now quantum field theory on curved spacetimes. There are actually several approaches which are compatible to one another, but they look different. And so I will, time permitting, discuss three of them: local algebras, path integrals, and canonical quantization. Let me say that the first approach is actually dominant in the mathematical literature, in recent mathematical literature, but the other approaches are actually also very respectable. So local algebras. I mean, there are several ways to describe them. Usually one starts with a star algebra generated by smeared fields. So phi hat means the field, and the f is the smearing function, which is and you assume that the commutator is defined by the Pauli-Jordan propagator, which you have seen already. And you also want to assume there's some self-adjointness condition. There is for lovers of C-star algebras, I don't know whether there are some here. There is a C-star version of this where you consider exponentials, but so this defines an algebra, but it is not enough for applications. We also need representation. Representations are obtained by the GNS construction from a certain state, and typically we want the state to be a Fock vacuum. Now, there are no there is no unique choice on a generic spacetime. If the spacetime is stationary, there is a distinguished choice, but not in the generic case. Now, on the other hand, if we take any state, we get some stupid. I mean, this can be non-physical. It is more or less agreed that one should use states which satisfy the so-called Hadamard condition. So, in other words, one should fix a two-point function that, which defines the state. So here, the state is denoted omega. Its one-point function should vanish. The two-point function should be given by this Whiteman function, and higher endpoint functions are obtained from the two-point function by the usual rule for quasi-free states. So that's So, and this is about this was the first approach. Now, actually, okay, let me go to the second approach. Now, I mean, the result of the first approach was that we constructed an algebra and its representation. Now we have a different philosophy. We want to compute the scattering matrix. Scattering matrix, so there are two philosophies that can be used. One is the path integral approach, so which uses the Lagrangian. So the free Lagrangian is given by this. So the free Lagrangian is quadratic in fields. So there is the kinetic term, which is defined by the metric. And there is the scalar potential. And then you integrate this over the spacetime. So this is everything here is in coordinates. So this is this measure is invariant on spacetime. You can also add a source. So source is called the J. And then the generating function of the free theory is formally given by this expression, which mathematicians often say that it is ill-defined because there is no measure. I mean, you integrate, but there's no measure. I will refute this statement. In reality, there is a clear interpretation of this this expression. And here is an elementary fact about Fresnel integrals. So suppose you have a matrix, a real matrix, and I mean finite dimensional matrix. Then this is sometimes called the Fresnel integral. So you have a variable u, the t denotes the transposition, and you add a source term. I mean, well, this is not Lebesgue integrable, but in the sense of some, I mean, of an oscillatory integral, this you have the following rigorous formula. Now, the action can be formally rewritten as a quadratic expression with this operator. Well, now it is infinite dimensional, but so what? Suppose you can interpret it as a closed operator on L squared of the spacetime. For instance, if it is essentially self-adjoint, then we define this to be with this formula, which is a direct generalization of that integral. So at least for quadratic Lagrangian, there is no problem of path integral whatsoever. And here the operator, theoretic Feynman operator appears. I mean, the one that was defined at the beginning of my lecture, which we can add interaction, and then interaction means a term in the Lagrangian which has which is a polynomial, and then it is you can define the generating function of the full theory. You can expand it in Feynman diagrams, and you can compute everything, putting this operator theoretic Feynman propagator at each line. Of course, there is a problem with renormalization, but it is, well, it is understood how to deal with it. And you can extract scattering amplitudes by the LSZ formula, which, I mean, generalized to this setting. Canonical quantization, now needs time. So we assume that the Klein-Gordon, that the manifold is stationary. Let's assume that first that it is stationary. So there is time times space slice. Then actually the quantum field theory can be repeated as it is in textbooks. So you provided that we have stability. So this scalar potential has to be positive. Then we split into positive frequencies, negative frequencies. Nothing changes, and we get. So we get the Feynman propagator from this state, and it coincides with the operator theorem. So here the canonical approach is again equivalent to the path integral approach. The non-stationary case is more subtle because we don't have a unique distinguished Hilbert space representation. Now it is again we need to choose time, and it is convenient to assume that the metric has the so-called Arnovitt-Desser-Misner form. Now. You can do the same things. Now here we have the in state and the out state. They are different. And so the main difference is that we need to divide by the overlap. And in particular, we have the in-out Feynman propagator. We can add to the Hamiltonian a perturbation, and we can compute the scattering operator. And well, not everything is explained in the slides. In any case, I don't have time. But you get a formalism which, at least in good situations, which so especially if the space-time is asymptotically stationary and stable, then you get an equivalent formalism. Now, the important thing is that you always have to divide by the overlap. And I think, I think I will stop here. Thank you.
Thank you very much. Questions?
This on-cell formalism, the on-cell setting, is the same with this covariant phase formalism?
That may be so. I mean, terminology here can be very diverse.
I think about covariant phase space formalism.
I'm not sure if you, so it is a formalism for what? I mean, I think I heard a similar term for something, not for quantum field theory, but for computing the heat kernel. I mean, this is a different story, but related story. I think this is something else, but you can show me the place where it is.
Well, in the beginning, kind of similar. They also start from the solution space. They can introduce this Poisson bracket and do the quantization.
Okay.
Yeah, I think the taste is kind of similar to the concept.
I mean, here all formalism are equivalent, even though they look different. So yeah, maybe.
Maybe a second question, can you generalize this method to gauge theory, gauge field theory?
Okay. So first, QED. QED is a gauge theory. Yes, you can generalize this. I mean, I essentially spoke mostly about the linear field. I mean, I would not call it a free field, but a linear field because it's and you can do linear QED with, let's say, with external sources, more or less as I described. Now, you can also go, I'm not sure if this has been worked out fully, but I believe you can do it. Now, concerning Yang-Mills theory, I think, well, this is an interacting theory. I suppose it works as well.
Okay, thank you.
Questions? So I have a question. So do you know if one can use geometric optics or WKB approximation to find green functions that you talked about?
Yes. Okay. There exists a very well developed formalism to find these green functions, and I mean, yes, it uses WKB. I mean, there are various yes.
But this is it.
I have not been talking about methods to compute these functions. I assume I assume that somebody computed them for me. I mean, I was defining them, but not. I mean, there are methods how to find them.
Other questions? So let's thank the speaker again.